Okay, now I will discuss more on the experiment that are contained under the method verification. First, precision. It is a repeatability test which experiment which evaluate how much the method will give the same result if you test the same sample repeatedly. So there are few factors to be considered when you want to do this test. First, time period of experiment. If you use a short time only, then the effect of long-term variation will not be observed due to day-to-day variation. Example, temperature, electric, humidity, and etc. Second, matrix of sample. So the test sample should as close as possible to the real specimen. Usually in the lab, we use the individual patient samples or patient pool. And if you need to do the standard solutions or control solution, just make sure that this solution mimic to sample patient. Third, number of sample. It should depend on the concentrations that are critical for the medical use of the test. Generally, we use 2 or 3 concentration that are medically important decision level. And fourth, number of test sample. Ideally, we use the minimum 20 samples, and it is for better estimate of random error. However, due to cost and time constraint, we can apply CLSI EP15 procedure, which I will discuss more later on, which consume less sample and time needed. So for precision procedure, you can find it under CLSI recommendation. It got 2 procedure here, EP05 and EP15. EP05 is used to validate a method against user requirements and is generally used by manufacturer. Whereas for EP15, it is used to verify by user that the laboratory's performance is consistent with claims by the manufacturer. So, the laboratory can use EP15. I just described EP5 procedure in case if you want to use it. So, the procedure first, assessment is performed at least 2 levels of concentration, and each level is run in duplicate with 2 runs per day over 20 days, and each run separated by a minimum of 2 hours. There should be 1 QC sample in each run. The order of analysis of test materials and QC for each run or day should be changed, and it is to stimulate actual operation. Include at least 10 patient samples in each run. So for EP15 procedure, it is much simpler. The assessment is performed at least 2 levels of concentration. Just run 3 replicate sample over 5 days, and the outlier data should be removed in pairs and repeat the run. So the data that you obtain, you can calculate for mean, ST and CV. ST or CV then are compared to for acceptability. You can compare with the manufacturer claim. Usually we use manufacturer claim for precision experiment. You can use quality requirement criteria which I have explained in the part 1, such as biological variation, CLIA, European, and etc. Or you can use compare with the EQA criteria. This is the example of the data, yeah, under the EP15 procedure. So you run one sample. Yeah. So you run one sample. So each day you run in triplicate. So this one, run 1, run 2, and run 3 on the first day, and then you run on the second day until fifth day. So all the data you find for the mean, ST, and CV. For this one, we calculate for total imposition and within run imposition, and we compare with the manufacturer claim. This is what the manufacturer claim, and we find that our result, CV result, is much lower rather than the what the manufacturer claim. So with this result, meaning that the precision test is good and accepted. So it is the exercise if you want to use. Okay, I show you another example. This is for the test ALP. Yeah, we run for 20 days. This is for level 1, level 2, and level 3. This is we use the procedure of EP5, yeah, and then we calculate for the mean, ST, and CV. So for this CV, we compare with the biological variation. The biological variation is give here is 6.4%. Oh, sorry. We use the imposition. We use the imposition criteria, which is 3.2%. So our experiment, the CV is our data, CV data, each all are less than 3.2%. So meaning that the precision of our test is acceptable. So now another experiment, accuracy. So the accuracy, it is experiment, of course, for accuracy of the test. So for accuracy, we can use method, the experiment, we can use method comparison, which is we can compare with reference method or certified reference material or standard reference material, or if it is not available, you can just compare with the old method or that you already available in the lab. And another experiment for accuracy is recovery. Okay, I explain more detail for method comparison first, which we usually use for the accuracy determination. The analytical method comparison, the analytical method that is used for comparison must be carefully selected because the interpretation of the experiment results will depend on the assumption that can be made about the correctness of results from the comparative method. Ideally, we compare the method with the reference method. So, any difference between a test method and a reference method are assigned to the test method. However, most comparison study is between test method and available routine method in the lab, not the reference method. Therefore, any difference between test method and routine method must be carefully interpreted. If there is no significant difference, meaning that there is relatively same accuracy between test method and routine method. If there is significant difference, we need to check which one is not accurate using recovery experiment, interference experiment, or any other way. So these are the factors to consider if you want to do the method comparison experiment. First, the number of specimen must be more than 40 or equal to 40, and the specimen concentration should cover the entire reportable range of method and should represent the spectrum of disease expected in routine application. So this criteria is much more important than the number one criteria, single versus duplicate measurement. Common practice is to measure one time for each method. Ideally, we measure duplicate in two different cups in different run. It is to check validity measurement, sample mix-up, transport error, and etc. But however, if you are unable to do that, the duplicate measurement, you can use the single measurement, which run in both test method and available method or reference method. Time period. Several different analytical runs on different days is better than one shot in one day. Minimum 5 days recommended. Better up to 20 days, meaning that the period of doing this experiment minimum is 5 days or until to 20 days. So if you have much longer time or much budget, you can do 20 days. But if you have constraint time, constraint operator, then 5 days is acceptable. Thus, between day variation can be accommodated. The specimen stability, you need to run among methods within 2 hours. Shorter if analyte is not stable. Example, the ABG, arterial blood gases, you must run among the method as soon as possible, because stability may be improved. Some of the experiment stability may be improved by adding preservative, separating serum or plasma from blood cell, or by you fridge or using the freeze, because we don't want difference observed due to error in handling specimen and not due to systematic analytical error itself. So after you do the method comparison experiment, you will obtain the data, right? So there are many ways of doing the data analysis for method comparison, such as comparison plot or linear regression graph, Blunt-Altman plot or difference plot, and PET-t-test. I explain first on comparison plot. It is or linear regression graph. It is suitable for analytes that are not expected to show one-to-one agreement. Example, enzyme, protein, and usually we use this. We can use this to almost all the tests, quantitative tests, and the result that cover wide analytical range. And then the statistic allow estimation of systematic error at more than one medical decision concentration, and will show proportional and constant systematic error. This is the example of the comparison plot. So the y-axis is test method result, while the x-axis is the comparative method result or reference method result. Ideally should be there is no difference between the test method result and the versus comparative method result, which the equation is y equal to mx plus c. M will become 1 and c will become 0. And for the r, which is the correlation coefficient, okay, so if the r is 0.99 or larger, simple linear regression calculation should provide reliable estimate of the slope and intercept, and meaning that the data is enough. However, if the r is less than 0.99, you need to collect additional data to expand concentration range, or to consider to use t-test or use more complicated regression calculation. And remember, the discrepant result should be omitted. This one you need to omit it first before you continue to another step of data analysis. Okay, another graph, Blunt-Altman plot. Bland-Altman plot is used to observe outlier, yeah, and detect proportional or constant bias. So if you see here the Bland-Altman plot, for the y-axis it is the difference between the test method and available method or reference method, and for x-axis it is the mean of test method and available method or reference method. So from here you can check if there are any outliers. So before you continue another step of data analysis, you can remove the outlier data first, using this Bland-Altman plot, and you can detect if there is any proportional or constant bias from. So for this example, you can see there is constant bias, and yeah, it is constant bias because this is the mean. So it seems that the tested method giving the much lower result compared to the available method, yeah, or reference method. So from the data analysis, how to estimate bias error? So first, plot linear regression and calculate the slope and intercept. This is the equation. I'm sure you know this very well. Y equal to mx plus c, where the m is slope and c is intercept. And remove the outlier as I have mentioned before. And then calculate systematic error by using regression equation at clinicalization limit, and use quality requirements selected to judge the acceptability. So this one is the example of the data, and then you have plotted the regression analysis and you get the equation. So from this equation you use the medical decision limit, yeah. From this for HDL, the medical decision limit is 1.2 millimole and 0.7 millimole. So what happened is you use this data and you put into the equation, yeah, and you get the value of y, and then after this you calculate the bias. Meaning that this x data you minus with the y data and you get the bias, and you turn it into the this bias you turn it into percentage. How to calculate the percentage? This bias you divide with the x data and multiply with 100, and you get the bias in percentage. And after you get the bias in percentage, you can compare with the quality requirement. So for this example, I use the allowable bias waistguard. So don't worry about the negative or positive, just take the value. So for this example, the value is the bias is 1.7, and for second level is 2.8%, which is lower than allowable bias from the waistguard biological variation. So the conclusion is the difference between test method and the available method, there is no difference and acceptable. So meaning that the new method is accept and have the same accuracy with the available method. Okay, this one you can use yourself to study how to calculate the bias. Yeah, this is the bias and how to calculate the bias percentage. Okay, remember this is the medical decision limit. It is the value which the doctor used to do the decision whether the for HDL, whether the patient have good HDL level or the level is very low for the patient. Okay. Okay, so another way to do conclusion or judge the acceptability, you can use a quality requirement of allowable total error. So the allowable total error, quality requirement for total error can be obtained from Westgard table. So this is the equation: total error equal to bias plus 3SD. This SD or precision you can get from your precision study. Okay. So the conclusion, if the total error calculated is less than allowable total error, which is from the quality requirement, meaning that two methods have same relative accuracy and acceptable. If total error calculated is more than allowable total error, meaning that two methods have different accuracy and difference cannot be accepted. So the accuracy is not accepted if you're using the reference method. So you need to do the troubleshooting. Yeah. And for method comparison, you can use another new statistic analysis such as Deming method, weighted Deming method, and many more as listed here. Okay, sometimes when the data is too narrow in analytical range, you can use PET test such as for sodium, potassium, calcium, and etc. So if you do the PET test, if you get the result P less than 0.5, meaning that there is no significant difference. So your testing method have the same accuracy with the available method. So you may use the new method. If the less is if the p value is less than 0.5, meaning that there is significant difference, and the new method have different accuracy compared to the available method or uh, reference method. So meaning that you have to do the troubleshooting. So usually if you do experiment, or sorry, if you do research, you will be hoping that your p value is less than 0.5, right? Because you want something significant different. But for this method comparison, we really want p value is more than 0.5, meaning that there will be same accuracy between the new method with the available method. Okay. So if method comparison is used for estimating accuracy or bias error less than the total allowable error, accuracy is accepted. If more, meaning that total allowable error, if more than total allowable error, meaning that accuracy not accepted. If method comparison is used for estimating the agreement between new method and old method, if there is significant difference, meaning that reference interval should be reviewed, meaning that the normal value for the patient need to be reviewed, and clinicians should notify that the result may be different from the previously issued if you still want to go on with the new method. Now I want to describe about the recovery experiment. This is to estimate proportional systematic error. This is the type of error whose magnitude increases as the concentration of analyte increases. The error is often caused by a substances in the sample matrix that reacts with the sought for analyte and therefore competes with the analytical reagents. Factors to be considered under recovery experiment. First, volume of standard added. Volume of standard is small relative to the volume of original patient sample. Recommend not more than 10% because we need to minimize the dilution of the original specimen matrix, meaning that the one that we want to add, the standard that we want to add, is not more than 10%. So we still have a lot of specimen matrix. Second, pipetting accuracy. It is critical because the concentration of analyte added will be calculated from the volume standard and the volume of original patient specimen. So use calibrated and accurate pipette, and also we may need the experienced operator with good pipetting skill, right? Third, concentration of analyte added. Add enough analyte to cover medical decision level. Fourth, concentration of standard solution. Ideally, use standard solution with high concentration because analyte added use is in small volume. Number of replicate measurement. General, usually we use duplicate, but preferably it is we can use triplicate or quadruplicate if we have enough cost, budget. And number 6, number of specimen tested depends on the competitive reaction that might cause a systematic error. If to determine protein in serum, that will affect only few samples needed, at least 2 samples, 2 specimen. If to determine any drug metabolite effect, need specimen with different patient condition. So, how to do the recovery experiment? First, prepare the tested specimen in pairs. So, one specimen you need to do in pair. Okay. So, this specimen, one you need to add it with analyte. Let's say in this example, you are interested to test analyte A, then you add analyte A into the specimen, and then one added with water. Afterwards, you need to calculate the A added into the specimen with this formula: M1V1 equal to M2V2. Afterwards, measure A in both samples. You need remember this two is cover for one patient only, but it is made in pairs, which is one added with A analyte and one added with water. After you measure A in both sample, you need to calculate the recovery. So, how to calculate the recovery? Okay, we go this example. Let's say we want to test the calcium. So we take the calcium standard 0.1 ml of a 20 milligram per deciliter calcium standard is added to 1 ml serum. Remember, just 10% from the serum. So the amount of calcium added, use this formula: M1V1 equal to M2V2. Put the data that we have, and then you get the amount of calcium added, which is 1.82 milligram per deciliter. Remember, this experiment should be conducted in few specimens, at least 2. So this is the example of the data obtained after the experiment. So you use the sample A. This is what you get after you measure. First, sample A. This is the result of sample A after you add with calcium. This is the result of sample A after you add with water. And then you calculate the difference. And this is the sample B. This is the result of sample B after you added with calcium. And this is the result of sample B after you added with water. After you added with water and you measure. And you calculate the difference. This one minus this, you get 1.6. This one you minus with this, you get 1.7. This 1.6. Okay. After that, you calculate the recovery. Yeah, 1.7 divide by the number of the real actual calcium added, which I have shown in the previous slide, which is 1.82 milligram per deciliter, and multiply with 100. You make it in percentage. So you get 93.4%, yeah, for sample A, and you get the recovery of 87.9% for sample B. So the average recovery is 90.6. So the proportional error is 100 minus 90.6. You get the proportional error of 9.4%. So how to judge? Well, you can compare with the selected quality requirement, such as CLIA criteria, which define that the middle calcium reference range about 10 milligram per deciliter. So the allowable total error is 10%. So in this example, you get the recovery for calcium is 9.4, which is less than 10%. Therefore, the recovery is accepted. And you also can compare also with this one. This is the desirable specification, yeah, from Westgard, which is the total error is much tighter, so quite difficult to compare with. And this one is I'm not sure. This one from the EQA, RCPA. Okay, the recovery total error is 4%, which is less. So it depends on you. Which requirement do you want to use? So this is the exercise for if you want to do recovery experiment for albumin. So you can calculate. This is the albumin standard. So you can calculate the difference and then the recovery. Okay, remember the albumin is only 0.1 milliliter added to 1 ml of albumin. And then you can calculate all this, and then you can compare with the maybe Westgard criteria, Biochemical variation, or any other quality requirement. Okay, do you need a break? Okay, now we go to another experiment of verification, which is reportable range or linearity. Okay, for reportable range or linearity experiment, the CLIA definition, it is the span of test result values over which the laboratory can establish or verify the accuracy of the instrument or test system measurement response. So usually the linearity experiment is to check the maximum of a method can measure accurately, while the minimum that the method can measure accurately is done using the limit of detection or limit of quantification experiment. It is done by the manufacturer. Okay, under reportable range, these are factors to consider. First, can be adequately assessed by visual, so we can draw best fit line. At least 4 levels of concentration, preferably 5, but you can do more if you want. Material, you can use standard solution. Linearity sets from proficiency testing vendor or EQA vendor. Patient specimens, which is diluted or pooled. Spike pool may be necessary for TDM, therapeutic drug monitoring. Diluents, you can use water, saline, bovine serum as manufacturer recommendation. Okay, remember, must as manufacturer recommendation. So this is the procedure for, usually we use two sample. First the low concentration sample and the high concentration sample. The low sample, usually the concentration near to zero or near to minimal detection limit, and for high sample the concentration should near upper detection limit. And then between this low and high sample, we need to prepare between them the mixture of this part. First, 3 part of low sample added to 1 part of high sample, 2 part of low sample with the 2 part of high sample, and 1 part of low sample with 3 part of high sample. And all these sample need to analyze in triplicate or 4 times the CLI is for the CLI recommend. But usually in my experience I just analyze in triplicate because of cost and time constraint. Okay, so this is the data that obtained after you do the experiment. Okay, this is, you get the very low, yeah, the low concentration, and then the high concentration, yeah, the high concentration, and this is the between them, the mixture, yeah. 3 part of high concentration you add with 1 part of low concentration, so this is the result. 2 part of high concentration you add with 2 part of low concentration, and these are the result after you measure in triplicate. And same goes with this row. Okay, please take note that it is okay if the series of sample in this experiment include need low, yeah, the mixture of low and high concentration, yeah, and near high. However, I was concerned the performance on level of 100 and 110. Therefore, I made the dilution of 100 and 110 using the neat high calibrator, and I got 7 series of samples instead of 5. So how do I make this concentration? I use the equation, the formula of M1V1 equal to M2V2. Yeah? So this is the equation. If you want to make those dilution with specific concentration, so for this example I have 7, yeah, one low, yeah, 1 2 3 4 5, 5, and addition 2, yeah, 7 concentration, and I run in triplicate, and these are the result. So remember, you need to calculate yourself the expected value, yeah, from the calculation. So for example, for this example, the need low, the value is 0. Yeah, the value given in the insert is 0. So of course the expected value is 0 lah, not 100. Okay, and then the need high, that it is I refer the standard solution insert, it is 104.80, yeah, unit. So there is so I put the value here, it is given by the insert. Okay, and then this one I get the from the calculation, yeah. And then after you calculate, you get the concentration by the calculation, yeah. You plot the data, expected value versus the mean run, after triplicate run. Okay, and this is the graph that we can obtain, yeah. Plot the reportable range graph, which is the expected value is on the y-axis and measured value is on the x-axis, and do your observation. you draw the best fit line. From here, in this example, I draw my best fit line. Do the observation. So in this observation, actually the data is not deviated from the best fit line. So the data, all the data are accepted. So the reportable range, you can report, the reportable range is up to manufacturer claim or up to the experiment highest concentration. Yeah. So in this example, the manufacturer claim is the highest concentration, which is 114.48. If I'm not mistaken, you can refer to the previous slide. So if the data deviate from the best fit line, then you can check the total error. So how to calculate the total error? Okay, if the data deviate, how to calculate total allowable error? Okay, let's say in this example, I'm suspecting that the highest concentration of 114.8 is actually a little bit deviate according to my eye lah, not your eye. Your eye maybe you find it good. So I suspect it is not good. So I want to check the total allowable error. So first, you need to calculate the allowable total error. You can refer to the quality requirement. In this example, I use the quality requirement from Westgard Surgical Variation. It gives 30.2%. So this allowable quality requirement, you need to change into unit, meaning that 30.2%, meaning that you have to divide 30.2 divide by 100, and you minus with the suspected concentration. In this case, I suspect the highest, which is 114.80. So you get the allowable total error is about 34.67. And then afterwards, you measure your total allowable error on that concentration using this formula. Measured total error equal to bias plus 2SD. So you can use the SD from your previous precision experiment, remember? Okay. So for example, when I did the precision experiment, I got the SSCV of 10%. So if the CV is 10%, need to change into unit, meaning that 114.8 from 10% is 11.48 unit. So therefore, I put the 2SD equal to 22.96. 11.4 you multiply with 2, right? So the bias equal to mean measured minus expected value. You can refer to the previous graph, the previous data that in the previous slide, which is equal to 5.9. So the measure total error is use this formula. You put the data in this formula, you equal to bias plus 2SD. Then you get the measure total error of 28.86. So this 28.86 is less than 30 allowable total error, which is 34.67. Hence, the reportable range can extend up to the manufacturer claim, which is 114.80 nanomole per liter. So please take note that the CV in this study was obtained after precision study, and in this case the CV was 10%. Okay. Okay, that's all for the reportable range. Now we go to the reference range. It is also called as reference interval. So we use 20 individual sample. If 2 or fewer test results fall out outside the manufacturer claim, then the reference range by manufacturer can be accepted, can be used, meaning that you use 20 individual sample and then you test this sample. So if only 2 or 1 test of this individual sample a result fall outside from the manufacturer reference range, then the reference range set by the manufacturer can be accepted and can be used. But if more than two, then you need to develop your own reference range. Remember, need to use the normal subject, or else you can give the false conclusion, and you need to consider the exclusion criteria. Okay, another experiment for method verification, it is sensitivity and specificity. It is done on the qualitative test result. Yeah, and the method tested compared to can be compared to reference method, real subject, and available method. Sensitivity, the definition is the proportion of those with the disease who tested positive indicate how good a test is at identifying the disease, whereas specificity is the proportion of those without the disease and who tested negative indicate how good a test is at identifying the non-disease. So you can do the experiment. Yeah, you can select the true positive and true negative, and you test, you get the result, and then you plot into this diagram. Yeah, the one with you have to plot the one with have the disease or positive result, and your testing result say it is positive, you put plot it in here, and same goes with another area, and then you have to do the calculation. So this is the calculation for sensitivity, and this is the calculation for specificity. The sensitivity is true positive divided by true positive plus false negative, and then multiply with 100 because the result is in percentage. Whereas the specificity, the true negative, you divide with false positive plus true negative and multiply with 100. So how to interpret the sensitivity and specificity data? You can compare with the quality requirement, manufacturer claim, or any journal or textbook. So if your sensitivity and specificity result is less than the target performance, well, meaning that your method is accepted. So with that, I end my presentation with thank you. Okay.